Okay, we're very sorry for the problem. First, I'd like to correct the name of the university that is being announced ever since yesterday. It should be University of the Philippines, Cebu, not University of Cebu in the Philippines, because it's a totally different university. It's a university which is a private university. This one is a national university. It's part of the University of the Philippines. Okay, so I'm Robert Roxas. I'm the chair of the Department of Computer Science, and I'm here to present to you something which is probably very new to you about cyberfilm. I don't know, have you heard about cyberfilm before? No? So this must be strange to you, but bear with me. This is still an approach. No? We are still trying to work with this that hopefully will someday help us in our programming. So it says here, the title is Cyberfilm, a visual programming and learning tool. So it's a combination between programming and learning. So as we start, let me ask a couple of questions. What do you prefer to use or do? You have their text-based or graphics-based commands? Graphics-based, okay. What do you prefer to use or do? Read books or reading books or viewing videos? Okay. Next, what do you prefer to use or do? Typing codes or automatic code generation? So that's it. Now, we have a problem. We call this the representation gap. Okay? So it's the difference between between the representation that the brain uses when thinking about the problem and the representation that the computer system can accept. Okay? So what we have in mind cannot directly be encoded, cannot be put into the system right away. You have some kind of transformation. In fact, as we all know, the machines can only understand zeros and ones, right? So it's a big transformation. So we have some common problems as programmers, for example. If a programmer wants to learn a new algorithm, the tendency is he or she needs to read a lot of documentations like books or manuals. Is it correct? Okay. So that's the first common problem. Sometimes you don't have the books, and even if you have online books and if you have that downloaded and there's no internet connections, you cannot read. Another problem is, which is, of course, this is a good solution actually compared to books. We have the online documentations that come with a certain software and so on. And then it normally contains hyperlinks that point to other links, which creates a seemingly unending cycle. So you have noticed that you try to understand something and there's a hyperlink in there, you click, and then after that, that page has also a lot of hyperlinks, and then later on you don't know where to go back. Okay, so that's a problem. This is another problem also. Who among you made programs who never committed syntax errors? Nobody? Okay? Especially when you start working, learning the programming language. It's always a fact that you commit syntax errors because of your typing, maybe typographical errors, and so on. So I think we all know that these things can be minimized, maybe, or we want to change things. So we approach this using visualization. It's a study or a field of study that aims to minimize the representation gap. In other words, we want to move the system closer to the user. So our goal is to provide a programming environment where the users can just simply create programs by combining cyberfilms. So just simply combining them. And then the users can learn and understand algorithms by watching sample algorithms in cyberfilm format. Later on, I will show you some slides. And then, of course, we provide an environment wherein typographical errors, syntax errors, etc. are minimized, if not eliminated. Filmification is one of the approaches in visualization. So it's a visualization approach that employs film. This is patterned after the concept of the traditional film. We all know what a film is, no? So a film is composed of, it can be a combination of films, scenes, frames, or stills. Anyway, we have illustrations later on. So cyberfilm is a visual programming language environment where algorithms are rendered in cyberfilm format. Users can learn algorithm by watching frames in two possible views. Later on, we'll see what are these views. And then these films are supported by template programs. And then the code generation will be automatic. So all those common problems that we have can be minimized using this approach. So the architecture is like this. You have the system will have a film library wherein all the possible films that we created or prepared will be stored. The users will simply try to retrieve the films and then try to watch them using the graphical user interface. Wherein in the graphical or GUI, graphical user interface, you will just watch some animations, and if you want these films to be part of your program, you simply specify the variables, the parameters, and so on. And then, since the films have code or template codes already prepared, this will be added to your program if you already specify the parameters needed for a particular film. And then you can combine this with other films. Then you save them as a film file, and then when you generate the code, those codes will be the basis for creating the program. By the way, if you have questions, you can ask questions from time to time. I'm showing you the original filmification approach. Actually, this is based on my advisor's research. So they have this so-called active knowledge studio, wherein the nodes are represents node states with flash types. So what they use is the types of flashing. For example, you have the full flash, meaning a particular node is being executed. So it will just flash. And then half flash. So in that case, it's really to make decision. And then the contour flash, it's being accessed for reference. So sometimes in the matrix, for example, let's say you are comparing two numbers. Those numbers are being accessed, but you don't actually do some manipulations on those numbers, right? So that's the concept of being accessed or reference. And then the flash, the node with no flash, meaning nothing is ongoing there, no processes at all. But this approach for me is not very good because of the limitation. If you have a lot of nodes and then you will see it like this, later on it will be difficult for you to distinguish the different types of flash. So I modify this and we use the flowchart symbols, modified flowchart symbols. So because since all computer science students, even IT students know about flowchart symbols, so it will be easy for us to understand what's going on in a particular frame. So these are the types that we employ. We still have the regular node with no shade or no color, it's not being referenced or accessed. So just like the old system. Then for the one that is accessed, it's really fully colored, not just a certain dot in the middle, just like the previous one. So you can see that this is being accessed, no? Fully colored circle one. And for the process, I think, what's the symbol for process in the flowchart symbol? Do you know? Process. Flowchart symbol process. It's just a rectangle, right? When you make some computations, it should be in a rectangle. And since we want to have a uniform size of the nodes, so we compress it, make it into a square rather than a rectangle. But still, it's close to the original flowchart symbol. And then for decisions, when you do some comparisons, we use the same as the flowchart symbol. Okay? And for input-output, so it's longer, and we compress it into this symbol. So once you see this, you can already understand what's going on in a particular field. But of course, later on, you have to specify your formula. We also have a way of specifying formula. But for now, it's learning the algorithm, how it works. Then you can view some films. Anyway, I will give you some example later on. So let's go back to the cyber film concept. So these are the components, major components. Actually, we still have some other things that we can add. For now, I'll just give you at least three. First, the frame or the stem. It's the smallest element doing some useful task. So it can be like in a tree frame, or maybe a matrix or multi-stage network. These are just examples. Now, a scene consisting of one or more frames doing related tasks. For example, you are doing some computation like solving or getting the summation of n numbers. So you may use some of the films depending on the need. So as you see, it's a combination of, it's a series of films of that particular type, because it's the scenes or the frames are doing related tasks. Then for the film, it will be like this. You may have, for example, a tree computation, and then followed by matrix, then maybe a tree again, maybe multi-stage networks, and then matrix. So these are just an illustration. So you can now combine scenes to form a particular film. So you get the idea now. So let's have an example. For example, tree film. What are some of the computations that can be done on a tree film? I'll just give you three very simple examples so that you will have the idea. For example, we want to sum up numbers. No? We want to get the summation of n numbers. What's the running time? What's the running time if you sum up or you get the summation of n numbers? That's O of n. Right? Is there a way to speed up that computation? So, one way to do that is you will put all the numbers in the leaves. Okay? Put all the numbers in the leaves, and then you compute two at a time. No? It can be in parallel, so it will turn out to be log of n rather than n. So that's one possible use of tree film. So the system provides a sample film, small ones. And if it works for small ones, it will work for big ones. Just like when you teach programming or the faculty, or maybe the students learning programming, for example, about loop. I don't think you will be given a loop of 1 to 1,000 for just illustration purposes. Normally 1 to 5, 1 to 10, And if it works for these numbers, there's a guarantee that it will work for 1,000. So this is the same concept. We just have we will just give a simple example. And if you think this works, this is what you need, then you can take this and specify the parameters. Just like the loop, you may increase the number, the n. So if you use that the tree film, it can be like this. So viewing this, you can see the activities going on. What have you noticed? If the frames go from left to right, what happens to the processes? What have you noticed? It's going up. Okay? So you will watch that. And then you notice that you have there the circles filled with colors. So that means based on the semantics of this that I already gave a while ago. So a circle filled with the color means being accessed. And if you have a square, then that's doing processing. Maybe you add something. Okay? So that means in the second frame, you have two interior nodes doing computation. Okay? Process. And then below, the nodes are being accessed. And then the next frame, it goes up. And then eventually the third frame, it's on the top. So if you put a formula for this by simply adding the left and the right, eventually you get the answer from the root. And then you have there the summation of n numbers, right? So this is a illustration. This is an example. What else can we do with tree? Do you have an idea? Anything that we can do with tree? More or less the same as this, you can just change the formula. Any guess? Multiply? Yeah, multiply all numbers. The product of all numbers. Yeah. So you can change this actually later on. You can specify which formula you want. Now, how about giving the maximum and the minimum? Still the same process, right? So since we will be comparing, what will be the symbol that you will see in a frame? So it will be something like that. Although we are still studying the possibility of modifying a little bit, wherein after the decision, we insert the process wherein you say the maximum, the minimum. So this is just an example, and then we're trying to find a way, because this is still an ongoing research. So that's it. That's for a tree. So I hope you get the idea now of what's the use of this. Now, you just simply watch, and if you think my computation is like this, then I will save this as my part of my film, and then you will be given the chance to specify what formula you want. There's also another way of specifying formula. Okay. I mentioned watching the films or the frames in two different views. So the first view is the tile view. Okay? In the tile view, the frames are displayed in a tile format. Okay? Users may need to scroll the display either up or down. And then the full screen view, film is viewed one at a time. In this way, the users may manually change one frame at a time, either backward or forward. So it says may manually, meaning you can just click a button wherein it will just continuously play, or you can also manually play one at a time if you want to understand how it works. So this is an example of a tile view. A tile view, using this, you have there the matrix, no? And then you notice there's a square in the middle, surrounded by four different, four different circles. No? Four circles. So meaning, what does it mean now? If you see a square in the middle with circles surrounding it, surrounding that square, what does it mean? There's a computation going on at that particular node wherein it accesses the four different nodes. No? The data of the four different nodes. This is another example of a tile view. So you have here, this one, you receive input, and then later on you decide where to send this input. Then, depending on the instruction, it will just move in the direction. Anyway, we have a little discussion on that later on. This is just for showing you the tile view. For the full screen view, it will appear like this. You have here, you have buttons below. You can press the play button. No? Or you can also, by the way, since this is the first one, the option is just to play forward or automatically or one at a time. Once you press the button forward, then other buttons will also be activated. No? So it's also dependent on the situation. So this is another example for the multi-stage network. Now, for the code generation, so I already mentioned that users view some film. Some film, not some film. Okay, then if the film is suited for the problem at hand, the user takes it as part of his software program. And then the users will be asked to specify some parameters, like the size or dimensions, no? And then etc. Then the system will already save the code for that. Then the code is being changed to affect the different parameters being specified. And then that will form the source code already. So let's have this example, Jacobi iteration method. I don't know if you're familiar with this. So it's a matrix, no? Wherein supposedly the center will get the average of the data with the surrounding neighbors. So normally we code this like this. You have there, for example, B, I, J. So you have to specify all this. And when you type this one, it's prone to errors. Okay? It's prone to errors. Sometimes you encode a wrong index. No? So it takes time. But here, if it's already in a film, you don't have to worry about the code. All you have to do is just simply read, and the code is ready for that. So the syntax errors will be eliminated this way. You don't have to type the code. This is just the test that one of my students did this. By the way, at this point in time, we use assembly language as the source code. No? And then my student tested this Jacobi relaxation technique using that system. Of course, this is just to illustrate. No? So, for example, if you have a 4x4 node, this is 5x5. So it will be like this. No? This is the first, if you notice that the movement is from there, move. So it will not compute the edges. No? It's just the interior nodes. So this one, I specified frame 2. I magnified it. So what does this mean? So at index 1, 1, it references 0, 1, top, no? 0, 1, and then 1, 2, 1, 2, 1, and then 1, 0. So that's the meaning of that frame. This is the continuation. until the process, the frame is over. No? I mean, the competition, iteration is over. My student tested this using this 4x4 matrix. No? Supposedly this is, what's this, decimal or real numbers. No? But for illustration purposes, we remove the decimal places, just the integer part. No? So my students tested this with this data, and then after the first iteration, the output of the first iteration is there. So meaning the matrix changes from the original to the output 1 for iteration 1, and then output 2 for iteration 2. So he was able to test that one. And then we also tested this with a 5x6. So the first one is 4x4, and it works for 4x4. Now 5x6 example. So still it worked. Now let's have another example, the multi-stage network. So this is the idea. You may have some films before that, and then this film supply data to the cells. No? So it could be the first cell, the first row, first column, and so on. And then, of course, depending on the instruction, it will be passed to the different nodes. No? And it will end here, the right side. And then the result may be possibly sent to another film. So, to understand how it works, for example, the cell data, the cell receives the data and is then written into the memory of the cell. Now, the question is if the cell is the cell placed at the last row. So, if it's already the last row, meaning no need to decide, no? Because it's the last. Not last row, not last row, but last column, last stage. So if not, you go to step 3. Now, it reads the instruction bit by bit. If it's a 1, it goes to a different row, depending on based on the arrow, where it points. And then if it's in the same, if it's a 0, it will be just in the same row. And then you look until it reaches the last column. So to make it understandable, the student makes two illustrations. He made something like this. Using the command prompt, he ran the executable file, and then given some, including some inputs, for example, 1, it produces this cyberfilm counterpart in the UI. So, for example, this one, 1. So, in the first frame, second frame, you have there, it receives data, and then after that, it decides, okay? Then, since it's a 1, it passes the data to the third column because it's being linked by the arrow. No? Then, at the fourth frame, it decides, on a fifth frame, it decides where to send the data. Since it's a 1, it moves to the other row. For another example, 0, 1. Okay? 0, 1. So since it's a 0, after deciding, the data is passed to the same row. So number 5 and 4. And then from frame number 5, it decides where to send the data. Since it's a 1, it passes the data to the next row. So that's the last frame. So that's just the illustration. So, in summary, cyberfilm is an approach that provides a programming environment where the users can learn and understand algorithms by simply watching sample algorithms in cyberfilm format. So in that way, it is a learning tool. Now, you don't have to consult books. You just simply watch, and then once you learn, I think this is what I need, then I will take this as my own, and I will supply the needed formula and other parameters. And then, since it's we can create programs by combining fields, so of course it's a programming tool. And then the typographical errors, syntax errors, etc. are minimized if not eliminated. So my presentation ends there. So any question, clarification?